Hello everyone, I am Runzhou Tao from Columbia University, and I will talk about our paper Gleipnir toward practical error analysis for quantum programs. This is joint work with Yunong Shi, Jianan Yao, Chong, Frederic Chong, and Ronghui Gu. As we all know, quantum computers are very powerful in many important tasks, such as factorization, chemistry simulation, and machine learning. However, quantum computers are noisy and quantum states are vulnerable to various types of errors. The fault-tolerant quantum computing, where we can correct all errors by error-correcting codes, is still in the far future. Where we are now is the noisy intermediate-scale quantum or NISQ era. And in the NISQ era, error analysis of quantum programs is essential. To analyze errors in quantum programs, a typical framework will take the quantum program, the input state, and the noise model as input, and output an error bound about executing the program with the given input state. There are two naive ways to analyze errors in a quantum program. The first one is to directly compare the difference between the noisy execution result and the perfect execution result. This method gets the exact error, but is extremely inefficient or infeasible because computing the perfect result itself requires exponential classical time or a non-existent perfect quantum computer. Another way is to use some worst-case error metric, such as Deltanorm about the noise model, and add the metrics together. This method is efficient, but may overestimate too much because it only considers the noise model but not the program state. Logic of quantum robustness improves the previous approaches by incorporating the information of the program state to reason about errors in quantum programs. The logic produces logical judgment that deduce the error bound epsilon for a noisy program P when the input state satisfies some program predicate Q and degree lambda. However, it is still open to practically and automatically find such a non-trivial predicate. Consider this sequence rule in the logic of quantum robustness. It is unclear how to obtain a quantum predicate Q2 that is valid postcondition after executing QP1, while being strong enough to produce useful error bounds for P2. In this work, we propose Gleipnir, the first practical error analysis framework for quantum programs. First, we introduced the rho delta dimer norm, which is a new error metric when the input quantum states have a distance at most delta from some approximated state rho. This error metric can be efficiently computed using semi-definite programming given rho and delta. Second, to obtain rho and delta, we use Tensor Network to approximate the quantum states. Tensor Network is a graphical representation of tensors inspired by category theory. Our tensor network approach is adaptive. The precision of the approximation can be adjusted by varying the size of the tensor network so that tighter error bounds can be computed given greater computational resources. Finally, we develop a lightweight quantum error logic based on the rho delta dimer norm. Given the tensor network computation result in the previous step, we produce the judgment which states that the error of the noisy program P is bounded by epsilon when the input state is constrained by rho and delta. Now we introduce the workflow of Gleipnir. Given the quantum program and the input state, we first use tensor network to approximate the quantum states. Then, together with the noise model, we compute the rho delta diamond norm using the semi-definite program solver. Finally, we use the quantum error logic to get the final error bound. The rho delta diamond norm is defined as the maximum distance after applying the two superoperators on the same input state, where the input state has at most delta distance from rho. This norm can be efficiently solved by a semi-definite programming solver, given rho and delta, and this is the error metric used throughout the Gleipnir work. The quantum error logic produces the following logical judgment, which states that when the input state's distance to rho is less than delta, then the error is bounded by epsilon, or equivalently have rho delta diamond norm at most epsilon. There are 5 rules in the logic: the skip rule, the gate rule, the sequence rule, the weakening rule, and the measurement rule. Most of them correspond to the syntax of quantum programs. The skip rule says that skip produces no error. The gate rule says that error produced by a single gate application is bounded by the rho delta norm of that gate. The sequence rule says that if the first part of the program produces error epsilon 1 and the second part of the program produces error epsilon 2, and their rho delta is connected by the tensor network approximator, which we will explain later, then the total error of this noisy program is bounded by epsilon 1 plus epsilon 2. The measurement rule said that if the error in each branch is bounded by epsilon, then the total error is bounded by the probability to go into the wrong branch, which is delta, plus when the branch is correct, epsilon. We also had the weakening rule, which states that when the precondition is weakened, the bound still holds. Let's show an example using the logic of quantum error logic on the GHZ circuit with input state rho. We first compute the rho 0 diamond norm for the H gate. Then we apply the gate rule to transfer the norm to the logical judgment. Then we run the Tensor Network approximator and get rho hat delta, which is the approximation of the quantum state after executing the H gate. Then we compute the rho hat delta diamond norm for the C0 gate and apply the gate rule. Finally, we can apply the sequence rule to get the final error bound. Now we introduce the tensor network. Tensor network is a graphical representation of tensors. A node represents a tensor, and edges represent the indices of the tensor. For example, a vector is represented by one node and one edge. A matrix is represented by one node with two edges, and a superoperator, which is a mapping between matrices, has 4 indices, which is represented by a node with 4 edges. Tensor contraction is a generalization of matrix product. In the contraction, one index of a tensor and one index of another tensor is summed together, and a new tensor is formed with all other indices. Using the graphical representation, the contraction is represented by linking two edges together. For example, matrix product is the simplest tensor contraction, and contracting two rank 3 tensors will result in a rank 4 tensor. Gleipnir uses the matrix product state, or MPS, which is a spatial class of tensor network, to approximate quantum states. It uses two n matrices or vectors A10, A11, A20, A21, and AN0, AN1 to represent an n-qubit quantum state with this value. We can see that AI itself can be seen as a 3 tensor if we count the superscript 0 or 1 as the third index. Thus, the MPS can be represented as this string-like tensor network. To approximate the quantum states in the program using MPS, we first initialize the MPS to be the input state. Then we apply each gate in the program one by one and represent the resulting state as another MPS. In some steps, the resulting state may not be representable by MPS. We then use singular value decomposition and truncate smaller singular values to get an approximate MPS of the resulting state. After applying all gates, we get the final MPS as rho and the truncation errors adding together as delta. The running time of the approximation algorithm depends on the size of W of MPS, and larger W will give us a better approximation. Our experiments show that Gleipnir produces 15% to 30% tighter bonds than previous method. For example, for quantum programs IC model 45 and QAOA 75, which has 45 and 75 qubits, Gleipnir's bonds are significantly tighter than the worst-case bond, while using a full simulation with logic of quantum robustness will time out. We also show that Gleipnir can be used to guide noise-aware quantum compilation on a real quantum computer. That's all. Thank you.